All right, so in this section, we're going to do several things. We're actually going to do a lot. We're covering these two sections as one, and then we're going to also cover 13.3 and 13.4 as one section. This might take us a period and a half, though, whereas the other one won't take us that long. We're going to talk about simple harmonic motion. We're going to talk about the force applied, velocity, and acceleration on the object. We're going to talk about the parameters that actually describe it, like amplitude and frequency and those words. And then we're going to talk about the period and frequency specifically and calculate them. That's where our math is going to come into play. So let's begin and recall this information. This is something that you know already. We just demonstrated this a moment ago. I'm not going to go into a lot of detail. But what I want you to recognize is the following. When this spring is stretched fully, the spring wants to pull back. When it's compressed fully, it wants to push forward. Whenever it's at the equilibrium position, there's no force acting on the actual object. Although it's moving, take a look. You see how there's like a tail? That's what this is, like a shadow, showing that it's moving. This is showing that it's moving to the left. Okay, because again, it started here. You pulled on it. It was like what I just did a minute ago. I pulled on that actual mass and let go, and then it started to move. So you pull on this mass, and stretch the spring, and then let go. When you let go, it's going to move naturally back this way. That's what this is showing. These are little snapshots along the way. Okay, and this was our formula for Hooke's law from earlier in the year. You're going to need it for your lab. Okay, and it's a formula you should know, especially even for this section. So you have to make sure that you recognize that although this was earlier in the year, this is something that is going to be on this next stuff coming up. So this is the diagram that can be a little bit confusing. So let's go through it one step at a time. We talked about earlier, we talked about this. Let me go back to this guy actually, if I can. Here it is, yep. So we looked at this diagram here, this animation of Hooke's law, and what we said was when it was at its extremes, like there, we stopped it, and we saw that there was a lot of force going back. But what do we also know? When the object gets as far as possible and then starts to come back, what does it have to do to come back? What does it have to physically do? So it's moving this way, it's moving this way, it's moving this way, and then can it just start moving that way? What does it have to do before it can start moving that way? It has to physically stop. So at the ends, it has to have a velocity of, again, what is it? 0. But when it's at that equilibrium position, right there, oops, that's a bad pause. I wasn't on the stop sign. Hold on. Okay, right there, when it's at the equilibrium position, although the spring is neither stretched nor compressed, it's moving. It has velocity. And then what happens? It continues to move, slows down, stops again. And that's where it stops right there. So where are we seeing this? Let's go back to our slides. We're seeing this in these diagrams here. So we just saw it in that animation, but let's take a look at these diagrams now. So when this is pulled as far right as possible, it means that there's a lot of force acting on it. The spring wants to pull back that way. If there's force acting that way, what must there also be acting that way? If there's force, there must be what? What is it? Acceleration. Very good. Very good, Tiana. F equals ma. We know that the force acting on an object is proportional to its acceleration. That was Newton's law. So as a result, look at the first, third, and fifth scenario here, please. Look at row 1, row 3, and row 5. In all of those scenarios, you see that there's a force, right? And in all of them, there's also acceleration. Now, you notice the opposite in scenarios 2 and 4. Who can explain that? In scenarios right here, this scenario, number 2, and number 4, why are these different in the values than these 3 were? Jack?
Because they're both accelerating. Because they're both moving.
Moving. Good word, Jack. Very good. They're both moving. So they have to have velocity, whereas earlier the velocity was 0 because it stops. It stops. It stops. But here in the middle, you can see the tail. That tail is there to show you that it's moving left until it compresses. Then it's here. Then it starts to move right, and that's when it's here. Then it continues to move right, and that's when it's here. So what you're noticing is that at the equilibrium position, we have a lot of velocity, but no force or acceleration. And this is very, very counterintuitive. Because if you hear that an object has a lot of velocity, or an object is accelerating, you would put velocity and acceleration kind of together, right? Don't you associate them with each other? If you hear that an object is getting more and more velocity, you might say it's accelerating. Or if you hear that it's accelerating, it's getting more and more or less velocity. But in this case, we see that clearly in the middle position, There's no velocity and no acceleration yet. No force and no acceleration, yet its velocity is at a maximum at the middle there. Now, we've also seen this another time. We've also seen this with projectile motion. When you throw an object up in the air, right? You take this little weight here and toss it up in the air. What does it have to do at the top? It's got to stop. So at the top, what's the velocity at the very top? What is it? 0. There's no velocity. Yet there's still acceleration. You all know that. What's the acceleration always? Yeah. Okay, 9.81 downward. So the acceleration is there at the top, yet at the top there's no velocity. So where is that? Look at the diagram. Where is there acceleration? Because at the top there is acceleration, but there's no velocity. There is acceleration, but there's no velocity. Where do you see that? Where there is acceleration, but there's no velocity. Which location, Matt? Yeah, any. 1, 3, or 5, right? Bottom one, middle one, or top one. At any of those points, when this spring is stretched as far as possible, there's force acting, so there's acceleration, but there's no velocity. So when the spring is at the ends, it's like the object at the top of a parabola, or the top of a one-dimensional toss straight up and down. When it reaches that top, there's no velocity, but there's still acceleration pulling it down. It's like when the spring is stretched. When it's stretched fully, there's no velocity, but there's still acceleration pulling it backward. Okay, so again, I got to reiterate that this topic is applicable in so many ways. It is analogous to what we did with projectile motion with an object being tossed up and down. It is the same as a pendulum back and forth. It is the same as a rotational pendulum that you saw in the actual simulation or whatever that was called. Okay, so let's get back to this idea now, and let's take a look at the next slide first. So we talked about how a pendulum and a mass spring are similar, and I gave you that quick demo here, and I was saying okay, there's all potential, at the bottom all kinetic, at the top all potential, at the bottom all kinetic, and we see this with a pendulum. Well, how do you show that it's analogous? Look at this diagram. When the spring is stretched fully, it's like the pendulum is at the top. What kind of energy does the pendulum have again when it's at the top? What kind of energy? Potential. Well, if I stretch a spring, what am I doing to the spring? I'm storing potential energy in the spring. So when I stretch the spring, there's got potential energy in the spring right here. Well, you know what? This has potential energy also. Now, with a pendulum, when it reaches the bottom, what kind of energy does it have? When a pendulum reaches the bottom. Okay, kinetic at the bottom. The spring itself, when it's at the middle, well, there's no stretch in the spring anymore because it's at equilibrium. But it's moving, isn't it? When something is moving, it has kinetic energy. So we can see here that just looking at the energies, that these scenarios are going to be the same for all of them. When the pendulum comes back up right here, take a look at scenario 3, please. When the pendulum rises up, the spring now compresses. The spring now compresses. When the pendulum falls back to the middle, the spring gets pushed back to the middle. When the pendulum rises back up, the spring is now stretched. What's the big difference between these two? What's the big difference? Marilyn kind of gave it to us earlier. She hinted at it. What's the big difference between these two scenarios? Although the motion is analogous, the energies are the exact same thing. What's the difference here? There's one key difference we have to recognize. Yeah? What do you mean? Kind of hinted at it the right way, Travis.
Theta's involved.
Versus
Versus just the x direction.
Yeah. So this is a linear displacement. This is what? What do we call that? What is it? You said it before. What is it?
Angular.
Thank you. Angular. Very good. Angular displacement. Angular displacement. So when you're at max displacement for an object like a spring mass system, it could be maximum x, or if the spring is going up and down, maximum y. But for anything that's rotating, its maximum displacement itself is measured in degrees, or is measured by theta. Okay? There's a term for that. How many of you, raise your hand real quick if you play an instrument, or if you've played or currently play an instrument, or sing. I'll throw that in there too. Singing words too. Only a couple. All right. So if If for those that did raise their hand, you feel free to answer this, or even those that maybe don't play instruments can probably answer this too. If you pluck a guitar string, if you pluck on a guitar string, when it vibrates up and down, right? It ends up looking almost like a little curves up and down. It literally does that over and over, and then the string eventually dies off, and you stop hearing the sound. The hub or the drum of the guitar amplifies that sound. That's what the drum is there for. If you just take a string and pluck it, you'll hear it, but it won't be as amplified. So my question for you is, what is the term, or what is the phrase that measures how far the spring oscillates up and down, or the string on the guitar oscillates up and down, or the pendulum oscillates left to right? What's the actual term for that?
Amplitude.
Very good. Well done. Amplitude is the word we're looking for here. Okay, we're looking for amplitude. Now, the difference here is that the spring has a linear amplitude, measured in units of meters. Look at the mass. How far is this mass in equilibrium? Well, whatever this value is, say it's 4 meters, or 4 centimeters, or 4 something in length. Whereas with the pendulum, it's measured in degrees. So this might be 20 degrees or 30 degrees. Okay? All right, let's take a look at some of these terms. There comes amplitude in the next slide. So amplitude, the maximum displacement from equilibrium. Why do I put units vary? Because we just saw that. The units could be meters, the units could be degrees. Depends on what amplitude you're looking at in this case. Second is period. The period is the time it takes to complete a cycle. If you think about this, we talked about the period of planets. Planets pretty much, I shouldn't say exactly, but pretty much loop around with one cycle. Every time they come around, that's one period of revolution or one cycle. So if you recall from earlier, maybe you can jot this one down because you're going to need this knowledge. One cycle is technically when it gets back to where it started. So if you start at maximum amplitude, when it gets back there, that's one cycle. Okay? So for a spring, similarly, if I had a spring and I pull down and let go, the spring moves up, comes back down to here, that's one cycle. Okay, the time it takes to go through the full cycle. The frequency is the opposite, or let's say inverse actually. Let's write this down. It's the inverse of period. It's the inverse of your period. It's how many cycles occur at a given time. How many cycles occur. So for those that said they played music, or have sung at some point, frequency. Its units are hertz. Anybody want to explain where frequency comes into play a role in music?
The higher the frequency, the higher the pitch.
Very good. Frequency is pitch. Well done. Frequency is pitch in music. If the note you're playing is flat, what do? You're playing a note on a guitar, I play trumpet. On a trumpet, on any instrument really, so you're playing something, a note, and it's flat. What do you have to do?
You have to tune the guitar.
Yeah, you have to tune the instrument. You have to make it so that it's a little bit sharper. Okay, good timing, guys. We'll pick up with this tomorrow. We'll pick up with this slide right here tomorrow. A lot of this you should be able to understand, well, at least the period part of the pendulum you should be able to understand based on the lab alone. What do you notice? What is the period of the pendulum a function of? The period, we call this tau. Okay, the symbol is like the torque symbol. I'm going to go into the symbols in a minute, but what is the period of a pendulum a function of? Yeah, just the length. Okay, it's just the length. Recognize that it's not the mass. So you change the mass at the bottom, yet the period is pretty similar for those two, right? So this is the formula for the period of a pendulum. What does G stand for again? Yeah, 9.81. Now, if I was on the moon, well then G would change, right? So the period of a pendulum is a function of gravity and the length of the pendulum. Gravity and the length of the pendulum. So why does this make sense? All right, I take a spring and I expand it. Why does it want to go back? When I take a spring and expand it, why does it want to return? What am I doing? Physically, what am I doing, Mike?
You're pulling like the attractive force.
Okay. The molecules are, yeah, between them they're attractive. But what
You're creating potential.
I'm storing energy in it, and energy has to go somewhere. It wants to be transferred. So that energy would cause the spring to pull back, right? Kinetic energy. Well, when you take a pendulum and you raise it up, what are you giving it? What are you giving it? Potential energy. So in the case of a pendulum, gravity is the restoring force. It's what causes the pendulum to restore to its equilibrium position. In the case of a spring, K, the spring itself, is where the storing force comes from. So look at the denominator of both of these formulas. The G and the K, they're kind of similar in nature. The G is gravity pulling the pendulum back to the bottom. The K is the spring pulling it back to where it wants to be, back to equilibrium, where it's free length. So in both of these denominators, you have what gives the restoring part of it. The M and the L are the things that really matter as far as how long it will take. I mean, K does also, obviously. G doesn't matter much because we're really always on Earth. Obviously, for other planets or other gravitational fields, it would change, but not much. So it's really just L. Over here, it's K and M, but say we had the same spring several times with a couple different masses. You'd see that the mass clearly affects the time it takes. So take a look over here, because in your lab, you didn't actually do this. In your lab, you guys were determining the K value of the spring. And you were doing that, and you haven't done it mathematically yet, by measuring the stretch under a given mass. 50 grams, it's stretched. 100 grams, stretched. 150, stretched further. So you're going to measure the K value here. Now we're going to use that with that formula on the left. K being the spring constant, M being the mass that you hung. So the mass was 50, 100, or 150. Now, what we're talking about here, though, and I use the spring as a little bit easier, what we're really talking about here is what happens to the vibrations, the oscillations. So let me divide this mass. So if we release this and let go, we see that it takes a certain amount of time to oscillate back and forth. One full cycle is from where it started back to where it began, just like with the pendulum, back and forth. So again, when we talked about how these are analogous to each other, these are the formulas, and the formulas are analogous. That's what I kept going on about the first day, how this is like absolutely amazing to think about two completely separate and different systems. A pendulum back and forth, and a spring up and down. And then I also showed you the rotational spring. It would behave the same way. Okay? It would behave the same way. You would have a formula in the form of 2 pi root something over something. You would have the exact same formula with different parameters, right? We call these variables or parameters, the things that would change. So let's jot down the actual name. So this is called tau. Here and here, these are called tau, just like with torque, but it doesn't measure torque anymore. This is the time period of oscillations. So the time it takes for an object, as far as a pendulum, to go here and back. Okay, to go all the way across and then return. On the left-hand side, we're looking at the time it takes an object that's either compressing or expanding a spring to move forward and return. Okay, that's what we're looking at, the time it takes for this to occur. And you should know these variables at this point. You know M is mass. I shouldn't have to even say that. It's not meters because it's not a unit. It's a variable. Mass. K, spring constant. L, length of the pendulum. G, 9.81. 2 pi is a number. Okay, 2 pi is a number. Don't let that confuse you, please. I'm telling you now, there's a lot of mistakes. When it comes down to it, at the end of the problem, you're not going to leave things in terms of pi, like in your math course. And math makes sense to it. It actually really does. And later with math and physics, you can leave pi in there. But when you're using this to calculate data and values, you don't usually leave in terms of pi. If somebody said to you, how long do you think you run a race? And you're like, 3 pi hours. Would that make sense to say 3 pi hours? That's 9 point something hours? No, it wouldn't make any sense to use in common terms. Just like you wouldn't do that if you were actually coming up with a value. Now, in math, you're going to do proofs, you're going to do solutions that involve pi canceling. By not reducing or evaluating pi, and the pi's that drop off, like n cancels out. That's why you don't multiply out pi in math a lot, because it does reduce a lot later on. But in this course, 2 pi is just, in this case, 6.28. It's obviously a irrational number that goes on forever, but we can easily make the assumption 2 times 3.14, as far as values are considered. Okay, why can I do that? Because, I mean, look at gravity already. We only do 9.81, when in reality that's actually a lot further, the decimal approximation. Okay? The formula at the top. So now that we understand this, because we saw this in the lab, it made sense to start here. Now let's go up here. This symbol in your text is written as a lowercase f. The symbol means frequency. Now, the reason I don't use a lowercase f is because with f you think force. In physics, f means force usually. Now, in engineering, the symbol is omega. I've never seen f before. So I continued to carry that over when I started teaching physics, and then I saw physics textbooks start using lowercase f. It's the same thing. This symbol is called omega. Okay, it's also used for angular velocity. Okay, omega is used for both of those. All that I want you to see here is the relationship that exists. They are reciprocals of one another. Okay, when you see 1 over, they're reciprocal. So why does that make sense? What does frequency actually measure? What does frequency actually measure? I think we went over this quickly in the last class, but let's restate it again. Exactly. So there's a problem, or there's a scenario in one of your homeworks, but I'll give you a separate scenario. Let's say you're looking at, I don't know, a housefly. Have you ever seen a housefly move in super slow-mo? And you guys ever seen this before? It's wild. It really is. Their wings beat so many times, it's incredible. We're weaklings, if you think about it. If someday insects grow up to be the size we are, we get demolished. It doesn't matter how smart we are. They're so much stronger, it's unreal. They can flap their wings like hundreds of times every second. It's incredible. I mean, some of them thousands of times. Has anyone ever seen Honey, I Shrunk the Kids?
Yeah.
You seen it, Gus?
Yeah.
Do you remember when they encounter the ants and they're like huge?
Yeah.
And the smart kid, the little nerdy kid, is like, ants can carry up to 7 times their mass, so let's just jump on. And they end up, riding the ant. It's true. They're incredibly fast. Well, the frequency is how many times that bug can flap a wing every second. Okay, so if you think about frequency, think about how many times something occurs every single second. So the measurement of frequency is measured in hertz. Let's jot that down. The measurement of frequency is measured in hertz. So that unit of hertz here, Hz, is really just 1 over seconds. And I'm going to put a 1 so you know it's not an L. The same thing as 1 over seconds. And let me explain real quick to make sense of this. What are the units of the time period you were calculating during the lab? What were the units? How long did it take the pendulum to go back and forth? What were your units that you used? Seconds. So tau is measured in seconds. Well, simply put, if you want to figure out what the frequency is, omega here, you simply put in the number in seconds right here. So this has no units, this is the number 1, and this has units of seconds. So if I knew that the time period was 5 seconds, the frequency is 1/5. Well, it's really 1 over 5 seconds. But we don't say 1 over 5 seconds, like one cycle every 5 seconds. Instead, what do? We say hertz, 1/5 hertz. Okay, so imagine a pendulum that was, I don't know, from the ceiling down to like here. You raise the pendulum up, you let go. The time it takes to go all the way there and all the way back is 5 full seconds. That means that the frequency is 1 cycle every 5 seconds. I need you to read this with me so you understand, because frequency is something that people really just don't get. 1 cycle every 5 seconds. That's literally what it says. So when you hear a frequency of 1/5 hertz, it just means cycles per second, cycles per second, cycles per second. Okay, Mike?
So it's like 1.5?
Correct. So it'd be like the pendulum goes back and forth 1 time, and it takes 5 seconds to do so. Okay, in your lab, how long did it take the pendulum to go back and forth? About a second, right? It was about a second. So the frequency was about 1 hertz. Because it's 1 over 1, right? If the time period you calculated in the lab was 1, you put a 1 in the denominator, 1 cycle every 1 second, that's what 1 hertz is. All right? So I'm going to stop here at this point. So today's going to be all math stuff for this, okay? We did all the theory already. The lab that we did, it was all the theoretical stuff. Now we're really getting into all math. The first one is rather simple because I wanted to start you off a little bit easy. So you're given a mass of 20 kilograms. And I think in the other class I changed this to grams. Yes, I did. So let's change this to grams, please. Of 20 grams. It's connected to a spring, and it oscillates in simple harmonic motion. Again, what does simple harmonic motion mean? Anybody remember that term? Simple harmonic motion. It assumes something about this thing. What was the assumption made when it was in simple harmonic motion? What's something that we assume is usually not around even though it always is? It's usually gravity or something else. Not gravity in this case. Friction, yeah. Simple harmonic motion, if you recall, we had the apparatus set up the other day, was when you pull on a spring and you let go. What should it do? It should oscillate forever. But unfortunately, due to friction, due to loss of energy, what happens over time, those oscillations die down, and eventually that thing that's bouncing up and down, God bless you, comes to rest and stops. All right? So in these problems, we're assuming it's in simple harmonic motion, so there's no friction or oscillation loss involved. If we're told that the spring has a constant of 35 newtons per meter, determine the period and the frequency of the system. So this is straight out of your lab, really, right? In your lab, at the end of the lab, if you look at your calculations, look at number, It's in your discussion questions. If you look at your discussion questions, you could look at number 2. Number 2 on the discussion question, this would be a good example to help you with that on the lab tonight. So, in your lab, you were given a mass of either 50 grams, 100 grams, or 150 grams. And you knew what the K value, or you determined the K value from seeing how far it stretched. Now, what we're going to do at this point is to see how long does it take for this thing to actually oscillate up and down. And it works out that the data for this lab works out really well. If you really took one of these springs that we looked at and actually determined the time it took for these hooks to pull up and down and actually sat here with a stopwatch, it works out really nicely. And I think next year I'm actually going to include that as like a third part of the lab. So finding K values, doing the stuff with the pendulum, and then also with the mass spring. So when we pulled on that and let go, we saw it oscillated for a while. What we're trying to determine here is how long does it take, the period, to oscillate. And then the frequency is how many times does it oscillate every second. So if we can get one of those things, we can easily get the other. Okay, if we can get one, we can get the other, because they're reciprocals of each other. Period and frequency are going to be reciprocals of one another. So by looking at what I'm given, I write down first that I'm given a mass of 20 grams, which is 0.02 kilograms. Okay, in your lab, you were given different numbers, but it's no difference at all as far as what you're given. You were given the mass, same thing. In the lab, you calculated K. Here, I'm telling you the K value of this spring. 35 newtons per meter. So we've got the mass of the object, the actual spring constant. This object is released, and it simply goes up and down, oscillating forever in simple harmonic motion. The question is, how long does it take for one oscillation? That's what we're really looking for. And then once we know that, we can figure out, well, how many oscillations occur every second by just finding the inverse or the reciprocal of that value. What was our formula that we'd use here for a mass spring? What formula is it?
Is it tau equals 2 pi times the square root of L over K?
Yeah. Why isn't it square root of L over G? Why isn't it square root of L over G? Why is it square root of M over K? What was square root of L over G? Where did that come into play? Square root of L over G. It's for a pendulum, right? And the pendulum had to do with the length of the pendulum cord that mattered. If you remember, this is where your labs help you on tests, guys. From the lab, you were able to easily determine that it was the length of the cord that mattered. You tried several different masses and it had no effect. You changed the angle, really no effect either. It had to do with the length of the cord for a pendulum. So for this problem, we can know right away that we have to use this formula because we're looking at a mass spring system. A pendulum system would have L and G involved in it. L and G, those two things. So right off the bat, you have to recognize what your formula is giving you. This is what I keep reiterating this because on your midterm I pointed out also. You have to know what your formulas mean. Right now this is easy because we only have 3 choices. Right? Go back. Let's make sure that we're clear on that. Period, 2 pi is a constant, M is mass, K is spring constant. So this is the period of a mass spring system. And at this point all you're doing is plugging in. Okay, I think that this is one of those chapters, and I mentioned this to the class, that students do really well in the math part of the test because it's not really like there's not many ways you can ask a problem like this. Okay, in a minute we're going to see that I use an example with like a bed mattress. And a mattress has springs in it. So really it's the same thing. You just model it differently. Or maybe a person jumps off of a bridge and he has a bungee cord attached to him or her. And as a result, the person bungees up and down a couple times in approximately simple harmonic motion. It's the exact same example, except now the mass would be probably like 20 grams. Oh, not. It would probably be like, actually in this case, it would probably be like 60 or 70 kilograms. That's the mass of a person, approximately. And then the K value would be the K value, God bless you, of the bungee cord itself. So this problem cannot be varied very much. Maybe sometimes you solve for mass. Maybe you'll solve for tau. Maybe you'll solve for K. So it's the algebra that you have to be pretty good at or trying to work through here. The actual application doesn't vary too much. Okay, it's a mass, it's a spring, and it's period. That's the 3 things involved in this formula. What do we get for tau? What do we get for the time period? What do we got? What is it? And what are my units for here? Tau measures time. Yeah, seconds. Okay, 0.15 seconds. Agree, disagree? Can I get just the verification of that? Agree? So if that's the case, and my follow-up question is, what's the frequency, I have to take the reciprocal of that. Just take your answer in your calculator and press x to the negative 1. Or just do 1 divided by that, obviously. It's the same thing. Okay, but whenever you want the reciprocal of something, in this case we want the frequency, and it's 1 over the period. 1 over 0.15. And it's going to be around probably a little less than 8 or something, right? What do you end up getting for it? 6.66. Oh yeah, true. A little less than 7. What are the units here? What are the units for frequency? What were the units? What were the units?
It's something over hertz.
Close. You had it. Say the second part.
Hertz.
Yeah, it's just hertz. And hertz are defined as something over seconds. So what this means, it means that the mass spring system will oscillate almost 7 times in a given second. Write yourself a note, please, right now. Because I tell you, 9 out of 10 students in this course end up not really understanding frequency well. It's something that seems to just baffle minds. This answer means that the mass spring system will oscillate almost 7 times. Vibrate, oscillate, go back and forth. Almost 7 times in a given second. In one given second, or in 1 second. And that makes sense because look, it tells you here that it takes only a fraction of a second to oscillate once. Remember, tau is the time it takes to oscillate once. If it's taking a fraction of a second to oscillate once, then it's going to oscillate several times in that 1 full second. So this would be like the example again. Remember, I think I went over this with you guys? Insects with their wings I talked about. An insect can flutter its wings hundreds of times every second. That would be a frequency of like 500. If it can do it 500 times in a second. Or somebody actually brought up the hummingbird. I forget which section. The hummingbird is an example of a bird that has a high frequency wing. Whereas most birds don't have a high frequency wing. They actually don't flap as quickly. Birds go like this. Or bigger birds for the most part. But insects have an extremely high frequency. That's why you hear even, what are they that you hear at night?
Crickets.
Grasshoppers or crickets, one of them that makes a chirping noise. It has to do with things being rubbed against each other at high frequencies. That's what you're actually hearing. I don't know if it's a defense mechanism to ward things off or it's something else. I'm not sure what the reasoning biology-wise is, but I know that it has to do with the frequency of oscillations occurring so fast that you hear it. That you're actually hearing what's going on around you.
Isn't that like how we talk too? With Facebook?
Yeah, so we're going to talk, really good analogy, Mike. We're going to talk in 13.3 and 13.4 about how sound waves propagate, and that's the same thing. When you speak, your vocal cords are straining, you have a certain frequency, but when you actually speak, you're vibrating the air molecules in front of you. The air molecules are vibrating in a longitudinal fashion until they reach your ear. And then your eardrum actually vibrates itself. Your brain interprets that sound. So if I started speaking another language, how many people in the room can speak another language? I'm just curious. Only a couple, all right. Fluently, obviously. I know you all take Spanish in other classes, but I'm just curious. If you speak another language to somebody and they don't know that language, are they going to be able to interpret? No, but they can hear it, right? So your eardrum actually is the thing that takes on the oscillations, or it almost absorbs the vibrations. But unless you know how to interpret it, your brain can't understand it. So you're always hearing stuff. It's whether or not you're actually understanding it or not. But it comes back to vibrations, like Mike was saying. When you speak, when you listen, all this stuff has to do with vibrations. Have you ever heard of something called string theory? Whether you know what it is or not, have you heard the phrase string theory? Anyone? Okay. String theory is this theory in physics that everything is made up of vibrating strings of different harmonics and different frequencies. The reason for that is because everything that has any sort of energy vibrates. Literally anything. Whether you see it or not, it doesn't look like these molecules in this desk are vibrating right now. But they actually are. They vibrate at a certain level, which give them a certain temperature, and that causes average kinetic energy and everything. So a lot of things come back to this topic of vibrations and frequencies. A lot more than what we're going to even touch upon in this course. But it can all be modeled with these equations. A little bit more complicated when we include friction, but the general equations are similar to what we're seeing here. Okay, so I want you to understand that although we're looking at simple examples here, this is not something that is used only for a mass spring. Who would care? Would you honestly care how long it takes a mass to oscillate up and down? No, it makes no difference. But it matters to you when you're in a car or when you're in an airplane. When you're in an airplane, there's a gust of wind. How come the airplane's able to settle itself? It minimizes those vibrations by adjusting flaps, by what's called a feedback system. It is able to adjust instantaneously so that these oscillations and these vibrations don't actually occur. So it really does matter a lot to you, whether or not you can see now that, like, who cares about a mass spring? Next time you're on a plane, think to yourself, oh, thank God for physics, or else this plane wouldn't stay up in the air. Unless we really understood vibrations and frequency and period and all this kind of stuff, it would not be possible to even fly in a plane, to even drive a car. Okay, all these things, all these mechanics that we're looking at, they're at a small level, but where can you go with them is what's really important. Let's go to the next example of this. If you're given a sample scenario where you need to design a pendulum, okay, so you need to design a pendulum with a given length so that it has a specific frequency. And why might this occur? There was when I was in grad school, there was a grad project that was funded by the Navy. It was a military program that they wanted to have engineers working in their military science from Villanova. And I was working with a professor who actually was designing an apparatus that you could actually send into situations where there's terrorists. So imagine there's like a terrorist threat or some sort of a threat to human life. This object worked by motion with pendula. It's amazing. There were like 7 or 8 pendulums inside of it. And in order for this object to roll on its own, there was a pendulum inside it that would control the rotational inertia. So if you wanted it to rotate to the right, a pendulum would actually slide to the right, and it would cause it to move that way. And then one forward, but it was a system of them that were all coupled to one another. But what it was able to do was able to navigate on its own and move, and it was a little object like this big. And it could sense how many people are in the room, what's the temperature, are there any gases in the room that are dangerous, is there something like a bomb nearby? It was amazing. This was one of the big projects, and they came up with this all via pendulum. Okay, it's kind of crazy to think about it. You're like, well, who cares about a pendulum? That's an application of this. So maybe you need something that has a specific frequency. So when you're designing stuff, you need to understand how to actually model things so that they come out with a specific frequency. Well, that's what we're doing here. A lot simpler though, right? This is just saying, what should the length be? That's it. So this is one part of maybe 1,000 questions that were asked during that graduate program that they were building that thing. This is like one question that they had to answer. Yet it stems back from your high school physics, really. So let's figure out what this is. So if we're looking at a pendulum here, we know that our formula is going to start with this. But the problem right away is that we have 2 unknowns. These are both unknown. We don't have the period, and we don't have the length. We know gravity, right? Gravity on Earth is 9.81. So thankfully we're on Earth in this case. When we're not on Earth, we'd have to figure out what gravity is. And we could actually use a pendulum to figure out gravity on a planet. So, but we're trying to find the length. That's the goal, to find L. So what can I do with this? How can I recognize that I actually have it?
You just find the inverse of 2.
Very good. The frequency was listed as 2. If that's the case, frequency is 2 hertz. But we know that frequency is the reciprocal of period. So we could just take 1/2 instead and use that for our period. Again, let me explain. 2 hertz means 2 oscillations occur. So 1, 2 in a given second. That's what that means. So if 2 oscillations occurred in 1 second, how long did it take for 1 oscillation to occur? Well, 1/2 of a second. Again, in 1 second, this happens twice. So for it to happen once, it takes 1/2 of a second. That's where the inverse part comes in. So if I want the period, I do the inverse of this. So the period is 1/2 of a second. Take that value and plug it in. And now you can solve for your L value. It's a little bit confusing to solve for L, so I'm going to go through the steps. Okay, we have 0.5 equals 2 pi root L over G. This says second, SEC. The value here of 0.5 and the 2 pi, they're just numbers. They're really just numbers. So don't let those confuse you at all. If you want to, start by dividing by 2 pi on both sides. Okay, start by dividing by 2 pi on both sides, and this will become 0.5 over 2 pi equals root L over G. 2 pi is a coefficient. Pi is a number. 2 is a number. Don't let them intimidate you because they're just Greek letters, like the pi symbol. So you divide by that quantity. How do you get rid of a square root? Yeah, you square it, right? You know this from your math course. You did radical systems this year already. You square both sides. So squaring both sides gives me the following. So I square the left-hand side. And when I square the right-hand side, it just gets rid of the radical. That's all it does. Well, what's g? We know what g is, 9.81. So now what we got to do is get rid of that g. Okay, and there's L. So whatever this number turns out to be, 0.5 over 2 pi, make sure 2 pi is in parentheses here. Take that quantity, square it, and then multiply it by g to get rid of g. So multiply it by 9.81. Okay, that'll give us the length needed for this pendulum to have a frequency of 2 hertz. That was the whole question from the beginning. What length should be designed so that this has a frequency of 2 hertz? How do you think, maybe let's see how many of you can really think outside the box. How do you think you'd be able to determine gravity, okay, on an unknown planet with only a pendulum? Sorry, I shouldn't say that. You have a pendulum, you have a meter stick, and a stopwatch. Those 3 things. Can you determine gravity on a planet?
Yeah, you just measure the length.
Good. That goes in for L. Keep going.
You just calculate the time to get a stopwatch of the period.
And then as a result, yeah, you get your g value. So even if you're on a planet and you had no idea about anything at all about the gravitational field, you could literally just take a simple pendulum because it's really precise. You saw your percent error. Wasn't it really low for this lab? Did you notice how much lower it was? Remember the one we did this way? The percent error was like 25%, right? But with the pendulum, didn't you notice it was like a small percent error? Because there's almost no friction involved there. There's very little loss of friction. So your answers were really precise. So you saw later on, I think it was later on in another question, in question number, or in part 3. Part 3 at the top of the second to last page said, verification of Earth's gravitational constant using a pendulum. That's what we were just talking about right there. So if you know the length of the pendulum, and you know the time it takes for it to oscillate back and forth, you can solve for g and come up with the gravitational pull. Now, your answer you get might be like 9.85, 9.7. It might not be exactly 9.81 because, again, we measured how many oscillations back and forth? At least 3 or 4, right? Did you measure a bunch? 3, 4, 5? Well, over those time periods, what's going to happen? Friction will have an effect. Okay, friction will have a little effect, so your data is not going to be perfect. But if you were in a situation where you could measure a perfect, simple harmonic motion object, you could easily come up with g to the exact value. Okay, and get that value. What does L turn out to be in this case? What do we get as a number? Tiana, go ahead. 6.05. Yes? No?
Yeah.
What else do we have?
I got 0.062.
0.062. Let's see. 0.5 over 2 pi, 1/4, 1/12, squaring that, 1/144th. I think it's probably this one, Tana. I think it's this one right here. Check your work real quick. Go through it again. Make sure your 2 pi, Tana, make sure your 2 pi is in parentheses. That's the common thing. Okay, do 0.5 over 2 pi in parentheses, then square it, and then 9.81. And I think this is it right here, because I remember saying 6.2 centimeters afterward. Well, again, if you're designing an experiment and you're coming up with a length, it makes sense to have it in something that you understand. So 6.2 centimeters, you know how big that is. But it's not necessarily it's not needed in this problem. It wasn't asked for.
Why does it say 6.5?
That we weren't sure if that was right. That was just a given one. It's this one here. You figure out what I'm saying? Okay. It's probably the squaring or the 2 pi in parentheses. One of those two, maybe. But the idea here is that I want you guys to see that we're doing a problem like this to show you how you can set up your own experiment. You could actually figure out the g value of another planet just by knowing L and tau. Those 2 things alone you could solve for a little g. Okay, so in your lab, when you do that tonight, make sure you solve this in a similar way. Look at the way I solved this. At this point right here, take a look. This is where you have g, right? How would you get g by itself if you were to do this in the lab later tonight? So you're at this point right here. How would you solve for g now? How do you get g alone if it's in the denominator over here? It's something that we can do. We've been doing it all year. If something's in the denominator and you want it, what can you do with it? Dividing by length would put a length over here, but it would still be 1 over g. G is still in the denominator, even if you divide by length. Close. That would work, but there's an easier thing to do.
What I would do is multiply both sides by g and then divide out the 0.5 over.
So inherently, what are you doing? Inherently, you're just...
Switching.
Yep. Okay, remember how it was like v equals x over t? We could switch these two spots? You could literally do that right now. So you could say g is over here and take this entire thing and put it in the denominator over here. Okay, it's just like v equals x over t, where you could switch diagonally. So if you have to go back and check your notes from earlier in the year, remember, these two variables could be flip-flopped. You can multiply by t and divide by v. It's the same thing as switching those entire things right there. Okay, that's just it's a little side note. That's all that is. But if I were doing it, I would probably switch this with this right here so that I get g by itself. Okay, flip-flop those two values to get g alone. Yes. All right. Let's move on to the next question. So now, in this one, this is a question that is on every subject test. It's on every math SAT. When something changes, what happens to everything? We've done it so many times this year. It's a little bit trickier though right now. There's one thing that makes this a little bit trickier. So we're trying to figure out, if I change the length of a pendulum by a factor of 4, how does the period itself change? How does the period itself change? And some of you probably know the answer right off the bat because you know how to do this with the formula. But let's go ahead and look at it. So here's our formula. Now, as always, if you want to, you can pick a number for L. Make L1 if you want to. Make L2, make it 3, whatever you want. And then change it by a factor of 4. So if you make L2, you get a number and then make it 8. If you make L5, then make L20 and compare those two. Or you can go through the way that we've been trying to work with, which is this. Say, you know what? I'm going to replace L with 4L. Because it says that the length increased by a factor of 4. That's the way I would approach this problem because I want to get through my test quick so I have time for my stuff at the end. I wouldn't plug in those numbers. Okay, again, you can do that, and some of you have been doing that, but it's really eating up a lot of your time on the test. The time it took me to just explain that has been 1.5 minutes already. And it would take even longer to plug in more numbers. If I read this problem on a test and I knew my material really well, I would start with this method. And I would say to myself, all right, well, what's the only thing that's different here? There's a 4, right? But where is that 4 located? Under the radical. So really, this is how I would write this. I'd write it like this. Why am I allowed to do that? Why can I take the root 4 and bring it out in front instead of leaving it underneath? And I'm not factoring things out like with multiple terms. What multiplication property tells me I can do that? Yeah, the commutative property. The commutative property tells me what's 4 times 5. It's the same thing as 5 times 4. So whether I put the radical 4 over here, anywhere, as long as it's in the numerator still, it's the same answer. So in reality, it looks like my answer is just double what it was to start. All right, see this? Here's your factor of increase right there. So again, by increasing by a factor of 4 in length, you've increased the period by a factor of 2, the square root of 4. And again, what if it had been a 9 instead of a 4, or a 16, or a 25? Why am I picking those types of numbers? Why am I picking 9, 16, 25? What am I doing? Yeah, I'm making it easy on you because it's perfect squares. So if this pendulum had gone up by a factor of 25 in length, its period would go up by a factor of root 25, or just 5. Okay, so for a lot of these problems, picking up on the concept saves you a lot of time. So if you were doing this on a test and you literally went right to this part here, and then you said, oh, that's a root 4 that's been changed. That's the only difference I see. Well, what does root 4 mean? It means 2. I've doubled the length of the period. You're done with that problem in like 10 seconds. As opposed to plugging in numbers, and it'll probably take you like 3 or 4 minutes. You might get the right answer, and that's good that you did. But you just spent like 4 minutes on a multiple choice problem that should take you 10 seconds. So do you see how when we talk about like when people struggle with finishing tests, I try to talk to you about how you optimize your time? It's the same thing with the SAT. You guys are taking, you've been taking PSAT and all this stuff, but you're going to take in May again the SAT as juniors, right? Are you all take it as juniors in May usually? Yes, no, maybe? ACT, SAT, depends? Okay. Well, you're going to take some sort of standardized test is what I'm saying. I'm trying to give you an idea of the fact that there are several ways to get to the same answer, right? Why take the longer route? Take the shorter or the more optimal route? Route. Ah, very good. I didn't see that. Okay? Route, right? Route 4. So in this case, it took too long for people to pick up on. That was good. For in this case, we see that this is the only change right here. Okay? Take the fastest way possible. Example 4 is the last one for the day. It might take us a little while to go through, which is fine. So, we're looking at a mattress. Okay? And if anybody knows what a mattress is like, you think of it as springs. And old mattresses, that's exactly what they were. They were springs. The bottom part of the mattress was what was called a box spring, and it was actually a box. I don't know why it's called a box spring, because there were actually no springs in a box spring, which makes no sense. It's that like a wooden piece of plywood, the material that held it up, and another piece of wood. And then there were supports in the middle to give it structural support. And then you put your mattress on top of that. And your mattress, if any of your families, like, if you live in an older house, or if you ever visit your grandparents, you lay on mattresses and you can actually find where the springs are. Like, there are actual physical springs inside of a mattress. Now, most mattresses nowadays, what are they? Yeah, like Tempur-Pedic or memory foam or all this like fancy stuff now, right? But in reality, what are those? They're just springs. They're not there, but they are. We talk about modeling physics, right? When I throw an object, we don't look at the full sheet, we just say it's a point, and the point is moving in space. We don't care about its thickness, its dimensions. Well, in this case, with a mattress, even if it's Tempur-Pedic, even if it's whatever these are now, those comfort ones that don't actually have springs, they can be modeled as if there were springs in them, because they have an elastic nature. Just like a rubber band. I've talked about rubber bands before in bungee jumping. A bungee jumping cord is not really a spring, but it can be modeled as a spring. If you've been at any amusement parks and you go on any of those kinds of rides, some of them actually do have springs. You physically see the springs themselves. Sometimes they're contained inside of the object, so you can't, manipulate them. But in this case, we're going to look at a mattress and we're going to say, you know what? Let's imagine that there's 200 springs inside this mattress. Even though there's probably a lot more, maybe like small springs, or even like a Tempur-Pedic, there's not springs. Let's say there's around 200 springs. Now, that's a big assumption to make. Even bigger assumption is this. A person is lying down on this mattress. Well, let's draw a quick picture of a bird's eye view of a person. Here's a person laying down, right? You get home, you flop down, you're tired, you want to lay there. Well, where are the springs? The springs are all over the mattress. So although there are 200 springs, you're probably not applying your weight on all 200. You're probably only applying your weight on some of those springs. But that's the way springs would be lined up in a matrix, right? So your body's not really being supported by all 200 springs. For the sake of the problem, we're going to say that 200 of them are supporting you, though. We could, if we wanted to, just say, you know what, it looks like only 50 are. You can pick whatever number you want, as long as your answer has some reasoning behind it. So for the sake of this, let's say that all 200 springs inside the mattress, maybe there's 600, but you're laying down, and 200 of them support your weight. 200 springs support your weight. Now, you're not given about anything with your weight. You're given your mass. The mass of an average person is around 70 kilograms. That's like 160 pounds. We're told that it takes about 1.5 seconds for you to, after you lay down, for you to oscillate back up. And that's a reasonable number, actually. If you think about, if you ever were to lay down on your bed, you just flop down on your bed. It'll take a solid second before the bed absorbs your weight and pushes you back up to where you would be at rest, at equilibrium. So we'll say that the time period is 1.5 seconds. Now, the problem is this. We're trying to figure out what the K value is. It says, determine a spring constant of a single spring. We're trying to figure out what the K value is, but we want a single spring. How much of your mass is one spring holding up? How much of your mass is one spring, Ange? Very good. Your mass is 70 kilograms. If 200 springs are actually supporting you, each spring supports a 200th of that. Again, imagine there were 30 of you guys holding up something in the room. Each of you would hold up a 30th of the weight, approximately, if it was equally distributed. Okay, so each spring holds up a 200th of your mass. So in reality, we got to do this. Divide that 70 by 200, please. That's the mass that each spring supports. Okay, that's the mass that each spring supports. The math is the easy part. It's the problem solving, doing this stuff that I'm talking about, that's important. So I sure hope you're really listening and focusing in right now. The value is going to be what? 0.35? 0.35 kilograms per spring. Oops. 0.35 kilograms per each spring. So now we know the mass that's being held by each spring. We know the time period it takes to oscillate back up. The question becomes, what is the spring constant? How big should these springs be? If you're a manufacturer, you're doing this. Engineers are designing beds. I know it sounds weird, but they're not just designing buildings and bridges. They're designing beds. How do you think Tempur-Pedic came about? NASA. You guys know that? So for all of those people that don't want to fund NASA, I'd say it's like 80% of actual patents today came about from NASA. It's absurd. All these different things that they did all their scientific testing on to have people up in space, a lot of it was done under conditions with no gravity, no friction, because you're in space. So a lot of patents today come from NASA. Teflon is a material that was used by NASA originally. So this idea of Tempur-Pedic and beds, you have to study. You have to understand what you're physically doing here. So that's what we're trying to show here, that this bed could be modeled this way. So if I want to figure out what K is, I got to go right to my formula. And here's my formula. The problem is that K is in the denominator. It's messy to solve for something when it's in a denominator. Okay, we got to go ahead and get rid of it. We got to get rid of the square root. So go ahead and practice this once. We've got 7 minutes. Try in the next 3 minutes to get an answer for me, please. It's not an easy problem, so I want you to actually try this on your own first. Maybe if you really get stuck, work with someone next to you, but try it on your own for a little bit first. Okay, 2 pi root m over k. Try to figure out what k is given the other information. If you're having trouble, I have to come by and show you too. You can, and then you can get square root k by itself and then square both sides. That works too. Yeah, I mean, it depends on how you're solving. If you're solving algebraically and you're not plugging in numbers, at some point in time you will have yeah, so I mean, you can either get rid of the 2 pi by dividing by 2 pi, and then you have the square root. You square both sides, or you can do what he's saying, which is like, you know what, put a square on the top, put a square on the bottom, and just move the root k over with this, this 1.5. Take the root k and 1.5 and switch them. The 1.5 is not in the radical. But either way works. It depends on how you want to do it. So if you want to solve it correctly, I would get rid of 2 pi first. Just divide by 2 pi. Yeah, so just think about it. 2 pi is a coefficient. This is like saying 10 equals 5x. Get rid of 5 and 5. Just divide this side by 2 pi. Hey, again, try, if you got it mathematically by plugging in numbers, try to do it with little variables too. A lot of you are really good with the numbers, you get it easy, but try with variables sometimes also, challenge yourself. You don't for this one, because you're given a period, 1.5. You're not, remember last time it was the frequency that was given last time. Correct. Yep, you're good on that. Hey, so if I were doing this with numbers, it would look like this. 1.5 equals 2 pi root 0.35 over k. I'd probably, you can do it several ways. Travers even mentioned a good point. He was like, you know what? He put it like this. He said root 0.35 over root k like that. And then he just said, you know what if I just switch the root k and the 1.5? That works too. See the root k right here and the 1.5? You can switch those just like you're switching other things. So you can do it this way also. This might make it even easier actually. And you get 2 pi times root 0.35 all over 1.5. Well, how do you get an answer? To get k by itself, you have to just square the whole side and square that whole side. So that's one way of getting your answer, doing it like that. I think that's a creative way to do it. I think it's actually easier probably. Okay, it's probably easier than taking the approach I took. My approach was I divided by 2 pi first, which left me with 0.35 over k. Then I squared both sides. And then I switched to k and that entire thing. Now, which answer is right? They're both right. It's the exact same answer. Okay, whichever number I use here, it's the exact same thing. And I know it doesn't seem like it is, but I guarantee it is. Because you're getting 0.35 here, and then that's going to be 0.35 once you square it. The 2 pi squared, that's in the denominator of the denominator, which actually bumps up to the numerator. 1.5 is squared, 1.5 is squared. So it's literally the exact same answer either way. Okay, if I'm solving this algebraically, I'll do that on the right side over here. It would be tau over 2 pi equals root m over k. I would, again, divide by 2 pi, square both sides, and then get k by itself. That's a way to do it algebraically. So any of these solutions work. Take this root in red, take the root in blue, or the algebraic solution in black. Okay, it doesn't matter. But you need to know your fractions. That's why when you're younger, you learn about fractions so much. You got to know your rules. Like when I see a denominator to denominator, I think that this number is really up in the numerator. That's actually what it is. Because dividing by a fraction means multiplying by the reciprocal, actually. So whenever you have a denominator to denominator, you can take that 4 pi squared and just bump it right up to the top there. Either way, what do you get for k? What do you get for k? Which simply means that it's going to take 6.14 newtons. That's a force. It's a weight, really. It's a force, a weight. It's going to take that much force to compress these springs a meter. Are you going to have springs that compress a meter in a bed? Obviously not, right? How big are springs in a bed? Maybe this big. So a meter we're talking about is up to here already. So if the springs are only about 10 centimeters as it is, maybe you want to convert this into newtons per centimeter so it's more realistic for an application of a bed or a mattress. But the idea is that this k value is the same no matter which way you approach the solution. Okay, so to stretch it by like a centimeter instead of a meter, you'd have to take a lot less. That'd be 100 different. So it'd be 0.0614 newtons per centimeter. So just think about the context of your answer, okay? Tonight, in order to practice this, you have this work tonight. You have the lab to finish up. I'm trying to think. I wouldn't get a head start on anything else, but if you want to, in the next day or two, start your problem set. The problem set's up for the next chapter, and the next chapter after that already. Okay, so feel free to get a head start on this.